let's talk about vector projections. So when we think about any vector, two vectors, u and v, they could be orthogonal, they could be parallel, they could be something in between. We can always split up the vector u into two separate vectors, a and b, one that runs parallel to v and one that runs orthogonal to it. So remember, if I just say a plus b, I get u. So you might think to yourself, why would we want to do this? Well, it turns out that projections are, or this little parallel piece to v, and also this little orthogonal piece to v, those two pieces are everywhere. They come up in physics, they come up in a lot of mathematics and even engineering, where you have quantities that cross over a little bit, and you really would like to find out a way to make them quantities that don't cross over. So this idea of vector projection is super important. So we want to be able to split u. We know that, it makes sense from the diagram, but we know we can split it into a and b. But the problem is, how do we figure out what that vector is, what that vector looks like? So what we do is we call a the projection of u onto v. So it's pretty simple. If you think about it, think about the way a projector works. If I were to stand above u, and I was standing at u and v, and I was looking down, I would see a shadow of u that falls onto v, and that's that idea of projection. So if I were to collapse u directly onto v, I would lose all of this data for b, and I would just have a. And that's the idea of why it's called projection. And this vector v, or b, is called the vector component of u orthogonal to v. Now that's not as simple or straightforward to remember, but you usually think of things in terms of projection and its complement. So anyway, what we know is that we have some vector a, and we know that it's parallel to v. So that's what we've got here. So if we know a is parallel to v, then we know that a has to be some scalar multiple of v, right? We determined that when we talked about parallel vectors. But how do we find what that c is? Well, let's use a little bit of algebra and some definitions here. So if we look at this triangle, we see that the vector a is the magnitude of u times cosine theta, right? That's the way the right triangle works. So then we could, since we know a is cv, we can pull out the scalar, and we know that's u cosine theta. And then if we multiply both sides by the magnitude of v, so I get magnitude of v squared over here, and I get a magnitude of v over here. Well, we've seen that before. Well, if we keep going down and we divide by that magnitude, we realize, well, wait, the magnitude of v is just v dot v, and the magnitude of u times the magnitude of v times cosine of the angle between them, well, that's u dot v. And since, remember, a is c times v, then a must be that projection must be that c value times the vector. So what you have is some scalar number, right? Because a dot product produces a scalar. Some vector times, or some number times the vector. This produces a scaled vector. Now, I cheated a little bit. I cheated on this step. Now, if you remember that the magnitude of CV isn't CV, it isn't just C times the magnitude of V, it's the absolute value of C times V. So why did I do that? Well, I did that because of this theta. Now, in the diagram, theta is between 0 and 90 degrees. So we know that it's going to be positive So we know that this is a non-negative number, right? It can only be 0 or positive. And if this was a known positive, that would have to be known to be positive. So in the case where theta is actually in that second quadrant, then what you find is that this value comes out to be negative. And so when we think about the way the absolute value works, we get a negative value and it kind of cascades its way through. So it still ends up working out, no problem. But I kind of cheated to make the proof a little simpler. Just sort of full disclosure there. And that's pretty much it for the way the projection works. We're going to be using this formula a pretty good bit. So buckle up.